talk of the day. The final talk will be given by Mbavhalelo Mulokwe. He was a PhD student at WITS, just freshly finished, and he will be soon be going to Pretoria for a postdoc. Mbavhalelo's talk is titled The Bilocal Approach to Critical ON Vector Model.
First, I would like to thank the organizers for the invitation to this wonderful school and workshop. And also, I would like to thank them for giving me this opportunity to come here and present my work, which is work that I did with my PhD supervisor, Professor João Rodrigues, on the critical ON vector model. The talk will be structured as follows. So I will first try to explain why, in the context of the ADS-CFT, we were looking at the critical ON vector model. And then I will give a brief introduction into the collective field theory with my main goal being to write down the collective field theory Hamiltonian. The ON vector model can also be described in terms of this nonlinear sigma model. I will introduce this nonlinear sigma model in terms of these collective bilocals and extract the two-point correlation function. I will then introduce the covariant two-time bilocals, and then I will show that the two-time description and the single-time description are actually equivalent. I will then introduce a very simple toy model, which will give us hints and clues as to how to proceed with the original problem that we were looking at. I will then discuss the presence of this delta equals to 1 and delta equals to 2 states, and I will argue that in the boundary that the delta equals to 1 state is actually kicked out from the spectrum. I will conclude the talk by giving a summary of the key results that I have obtained, and then I will then discuss certain open questions that I've been working on with Sylvester and Prof. Rodrigues. So this critical ON vector model, it has been conjectured by Klebanov and Polyakov that it should be drawn to minimal type A Vassiliev-Higher spin theory with scaling dimension delta equals to 2. If the Vassiliev-Higher spin theory has a scaling dimension delta equals to 1, then this should be dual to the free ON vector model. Now, the reason why this is very interesting is that in the light and limit, vector models are solvable. And because they are solvable, then this allows us to have a more detailed study of the ADS-CFT, and we can have a much better understanding of the working behind of this ADS-CFT correspondence. Earlier attempts at the bulk reconstruction were done by Untitled and Sumitas back in 2003. At the moment, there has been certain evidence or checks for this conjecture. The first one was the groundbreaking work done by Guillaume and Ying, where they computed and found that the three-point functions actually match on both sides of the duality. And Guillaume also did it for the free energy. There are also symmetry arguments due to Mandelstam and Mbavhalelo, who argue that if you have a single conserved higher spin current, then necessarily you will have an infinite number of them, and then your correlation functions are necessarily that of the free theory, meaning that it will be the free boson or the free fermion. But for this project, it will be interesting to note that there is also a bulk reconstruction due to Demirokhov and collaborators using collective fields, but in the literature there is also an alternative bulk reconstruction due to Douglas and collaborators using exact renormalization of flow. Because this Klebanov-Polyakov conjecture is of extreme importance, it has been generalized in different settings. For example, it has been conjectured that the Grosnev-Vaux model should be dual to type B Vassiliev theory. This is work done by Seskin and Sandel, Lee, and Petko. Vassiliev's theory cannot be formulated in flat space, but you can go ahead and formulate it in de Sitter spaces. And it has been conjectured that Vassiliev theory on de Sitter 4 should be holographically dual to the SPN vector model. This is work done by Stroming, Altman, and Ananios. There are also lower dimensional versions due to Gabardeli and Gopakumar, who says that the truncated Vassiliev-Pushkin theory formulated on ADS-3 should be dual to the WN vector models. Now, one thing that one can do is that one can take these vector models and couple them to Chen-Simons, and then in that case, it has been conjectured that Chen-Simons coupled to scalars should be dual to a version of Vassiliev that breaks parity. Another thing that I have been talking about type B and type A, I will then try to explain what these terms actually mean. So, but to summarize, what is classically known is that Vasiliev type A theory can have two different boundary conditions. If the boundary condition is such that delta equals to 1, then this Vasiliev theory should be drawn to the free ON scalar model. And then if the boundary condition, or if you change the boundary condition and replace it by delta equals to 2, then this should just be drawn to the critical scalar. A similar story will hold for the fermions, but with the boundary conditions swapped around. Now, for years, it has been known that there are various no-go theorems that tell you that you cannot have interacting higher spin fields. But Vasiliev, between 1987 and 92, gave us a yes-go theorem. And his theory is formulated in terms of the usual space-time coordinates. But in addition, there are these auxiliary twistor variables. Alpha and alpha dot will be going from 1 to 2. On these internal variables, then one introduces a star-like product, which is defined like that. And you can check that in terms of the internal variables, they will satisfy an algebra of that form. Before you get, so these Vasiliev equations then will be formulated in terms of these three master fields. It will be a scalar field B, a one form S in Z space, and another one form in space-time W. You can add this one form to form another master field A or A hat. In terms of this A, then Vasiliev equations can be written in, you can also introduce these Kleinian operators. But in terms of, what?
If it's on a memory stick, maybe that came up.
It's what?
If your presentation is on a memory stick,
Yes.
you just take it out. You can copy it to the
As I was saying, you can introduce these Kleinian operators. Once you have introduced these Kleinian operators, then you have all the ingredients that you need to write down in Vasiliev equations. I will just write them in compact form. They will be of this form. And one thing that you do notice is that I have introduced this notation pi acting on some field. Pi acting on some function of these twistor variables. It just swaps the signs of the unbarred variables, and the same thing with pi bar, it will change the signs of the barred variables. And one other thing that you have to notice is that these Vasiliev equations, they depend on this function f of b. And it turns out that by field definition, one can always put f to be of that form, where it will depend on some phase angle theta. Now, if you require that the theory should be parity invariant, then you only have two choices of that theta. Theta can either be 0 or pi over 2. If it's 0, then your f will be given by this. If it's pi over 2, by that. Theories which would have a function f of this form are called type A. Those which have a form of that are called type B. You can write them down in an uncompactified form. They will take that form. These equations are invariant under this transformation of that form. Once you have that, then you're looking for a solution. The simplest solution that you can get will be to just set B to be 0 and S to be 0 and take W to be of that form. Once you take W to be of this form and plug, the only equation that you will be left with will be this one, plug it back into that equation, and what you find is that the equations that you end up with actually describe ADS4. The first one will describe the torsionless condition for ADS4, the other one will be just expressing the Ricci tensor in terms of the field points. The other ingredient that comes into this vectorial ADS-CFT will be the ON vector model. ON vector model is a simple model which will have the dimension of that form. It has a trivial fixed point and an IR fixed point. But usually what people do is that they don't really work directly with that. They introduce an auxiliary sigma field, and using the Tractor-Novich-Hubbard transformation, you can rewrite this into a form of this form. And what you do notice is that then the action then becomes to be quadratic in terms of the ordinal fields phi A. For later use on, what I will mention is that sigma squared in the IR will be irrelevant, so you can work it out, and the action that you end up with will be the action for the nonlinear sigma model. And another point that I will mention is that because the action is quadratic in terms of the fields phi A, you can then integrate them out, and then you end up with an effective action in terms of the auxiliary field sigma. That's how people deal with the model. But one thing that you can notice is that if you look at the action, it depends on ON invariant quantities phi A. So it might be much better if we change the variables instead of working with the ordinal fields phi A to work with the bilocals phi A. Because in the initial case, I will be looking at single time quantization because I'm thinking in terms of the Hamiltonian. In that case, I will start by defining these single time bilocals. Because I'm in 3 dimension, x1 vector and x2 vector will be 2-dimensional vectors. Then what you can do is that you can count the number, a trivial counting of the number of degrees of freedom. This would be 2 plus 2 plus 1, so you have 5 degrees of freedom. And these 5 degrees of freedom together with their conjugate momentum have been mapped in the UV to ADS4 cross S1. This is work done by Mbavhalelo and collaborators. The map was originally done in light cone gauge, but it has been generalized to temporal gauge, again by Mbavhalelo and collaborators. In light cone gauge, it looks like that, but importantly for us is that the holographic direction will be given by something of this form. And what you notice is that it depends on the relative coordinates, meaning that the boundary which will correspond to z equals to 0 will correspond to when the case when x1 vector is equals to x2 vector, or when the 2 bilocals at the same point. And we'll make use of that later on. So to repeat, we start with a Lagrangian of that form. We change variables into these single time bilocals. This will introduce some Jacobian. In what follows, I want to just explain as to how that Jacobian comes about, or using collective field theory, how you get that. So the basic philosophy of collective field theory is that you start with the theory written in terms of some variables. I chose them to be as A. You do a transformation into, or you want to rewrite your theory in terms of other invariant operators, which is psi capital A. Your kinetic energy will be of that form. Using simple chain rule, you can show that this will be equivalent to that, where these operators, small omega A and capital omega A, are given as given above. I will use this notation of loop space, where capital omega, if you were doing this in loop space, capital omega used to join loops, and then small omega used to split them. So I will refer to capital omega as joining operator, and the other one as a splitting operator. You can look at the inner product. In the original variables, it's a trivial thing. But what then happens is that because you've changed variables, you introduce this non-trivial Jacobian J. You can try to make a field recognition, or you can try to absorb the Jacobian by identifying phi with J half phi. However, if you look at the derivatives, the transformation that you will end up having to do will be asymmetric a similarity transformation on the derivatives. Then if you do that, so you do a similarity transformation, and once you do this similarity transformation, you require that the kinetic term should be explicitly Hermitian. This gives you a differential equation for the Jacobian. You solve that differential equation, you will get, for example, for the ON, you will get the Jacobian that I gave previously. And it turns out that in the leading large N limit, the collective kinetic energy will be given by that. Then I will return to the ON vector model. In the ON vector models, I will be dealing with bilocals. You can quickly compute what is the splitting operator. You find it proportional to N. You do the same thing for the joining operator. Once you have these things, then you can compute the first part of the kinetic part, just depending on trace. J over d psi then would be the conjugate momenta. The other term will give you trace to the psi minus 1. Putting all these things together, then it means that the collective field Hamiltonian will take the form of this form. And as I was saying, J over d psi will be the conjugate momenta. But returning this form, the large N or the N dependence is not really explicit. So to do that, you can rescale. For example, if you take psi to N psi, d over d psi to 1 over N d psi, then your final form of the Hamiltonian will be looking something like this form. One thing to note is that this term will be subleading, so in the large N limit it will drop off, and you will end up with an effective potential. If you move back to momentum space, it will be given by something of that form. This then becomes simple to solve because you can just do a large N saddle point analysis. Doing that, you get equation of that form. You can try to integrate both sides of the equation. This gives you the standard gap equation. But it will be much simpler, or if we just call this parameter alpha, then express everything in terms of this parameter alpha. And then what we do find is that you end up with an equation of that form. That integral on the far right, you can quickly do the standard group integral, and in terms of our regularization, it will be with that form, but because we're interested in d equals to 3, z equals to 3, we take the expression, we put it back into the gap equation, we end up with a quadratic equation. In the infrared, we get that form. Now, one thing that this large N saddle point analysis has enabled us to do is that we have actually obtained the large N background. And the next thing that we want to do is that we want to expand about this large N background, meaning that we want to introduce fluctuations and do a systematic 1 over N expansion. Doing that, so I've said that. And then we take this expansion, plug it back into the collective field Hamiltonian, and then extract the quadratic Hamiltonian, which we found to be like that. One thing to note is that the traces appearing in this equation are functional traces, so I will highlight them out explicitly, and then just use Hamilton's equation. For example, take eta dot would be d8 over dp, work it out, it's given by that. Same thing with p dot. Now, because I want to diagonalize this problem, I have to take another eta dot. So I end up with eta dot dot. I will get a p dot, p dot, p dot, I replace it with this. Doing that, I end up with an expression of that form. Because I'm looking for the eigenfrequencies, I just Fourier expand. But one thing you do realize is that once you take eta dot, you get e squared with eta k1, k2, and then the other side of the equation simplifies to something of that form. The large N bilocals, I already know what they are, so I can write everything out explicitly. I end up with an equation of that form. I can try to simplify it. I end up with some integral equation for the fluctuations. But even before I try to solve this integral equation, the first thing that I need to check is that is this equation self-consistent? And to do that, I just integrate both sides. If I integrate this, it will be the same as that, so I will end up with 1 is equals to some integral. And if I solve this self-consistency equation, So I end up with an equation of this form. If I can solve this self-consistency equation for EP squared, then I will have found what are my eigenfrequencies. So I will take a detour and just revise the ON vector model. So the ON vector model will be given by an action of that form. Again, I introduce some bilocals, which are ON invariant. The case, the log of J will be given by that. And then I end up with an effective action in terms of these bilocals, where this term is this term is coming from the Jacobian. Again, I do saddle point analysis. I end up with some gap equation, and again, this integral is the loop integral you can do, but you end up with something of this form. So this alpha is an S parameter. At the conformal fixed point, you want it to go to 0. So this means that at the IR, lambda has to go to 0, and then your bilocals are given by that. Once you have these large n bilocals, again, it's the same story. You repeat it over and over again. You expand about that large n background, and you extract the quadratic effective action. This work has been done initially by Wu and Lang back in the 90s, but once you have something of this form, then you can get what your propagators are. Another thing that I do have to mention is that in order for me to get to this point, so that they decouple, is that I had to do a shift in this eters. Then you can move Fourier transform back to position space, and this is what you get. Now, one thing to note is that when I showed you that table, delta equals to 2 corresponded to the critical point. So this one seems to be fine because it has a conformal dimension of 2. At the boundary, I said that these two vectors have to be the same. So if you set them to be the same, this term and that term will be the same, but they will have a scaling dimension of delta equals to 1. So even Klebanov, in his original paper, does mention that there are certain shadowy operators that seem to be in the spectrum. What I want to do is that I want to show that that delta equals to 1 state has to be finishing at the boundary. But from that, from there, it doesn't seem clear. Then we can go back to the original phi squared squared theory. We introduce this two-time covariant bilocals. Same story, you write the quadratic effective action, but in this case it will be written in terms of some operator O. This operator O will be of that form. You do the standard thing, you want to invert it. This has been inverted by Mulokwe and Rodriguez back in '96. Antal and Sumit Das also used it in the early reconstruction. But the thing that you notice is that it will depend on some intermediate integral, which in 3 dimensions will just give you 1 over AP. But the thing that you have to notice is that the structure of this propagator is that this is the free, it consists of free propagation and some S-channel scattering state. So this propagator consists of a free disconnected piece and an S-channel scattering state. Since we will be interested in the on-shell condition. The on-shell condition, as usual, will come from looking at the pole of the propagator. So the equation that we will end up with will look something of that form. The first thing that you have to notice is that lambda, or the top coupling, has to be negative. And even if you were to square everything, you find that you end up with a tachyonic state or a negative bound state. Then if you look at what happens at the infrared, meaning you take lambda to infinity, then in the vector part,
take out the cable once.
Just keep the video.
So in the infrared, what one does find is that the bilocal propagator is actually finite. And if you were to amputate the legs, you find that the propagator will have the signature of the delta equals to true state that we found. So this in agreement up to the factors in the delta equals to 2 channel with the results obtained from using the 19. So far, I've been discussing two-time bilocals and single-time bilocals. Now I would like to show that these descriptions are the same. The first thing that I will try to do is look at the equation of motion, which is O eta is equals to 0. That gives me an equation of that form. Again, I do the same story. I look at the self-consistency condition, meaning that I just integrate both sides. This integral will cancel that one. We just end up with 1 equals to something. The question is this whole condition or self-consistency equation the same one that I obtained when I was looking at the single-time Hamiltonian approach? And in order for me to do that, what I do is that I just have to show that. So I can start with this integral. I will split it into k vector and dE. If I do the integral over dE, I get the complicated stuff that I got when I was doing the single-time approach. If you go back to the equation of motion, which is that expression, and you write it in coordinate space, what you find is that it gives you some partial differential equation involving some Dirac delta function in terms of their relative coordinates. Now, this equation recently has been solved using conformal partial ways by Mulokwe and collaborators, but we are not at that. What we want to do is that it's much simpler. We just want to come up with a toy model which will have certain properties of that thing. The simplest toy model that we can come up with is a contact mechanical problem, which will involve a Dirac delta function. So this V0 then will be playing the role of the Toff coupling, and because we're interested in the IR, we want to see what happens to solutions of these equations. For example, once we take the V0 to go into infinity. Now, if V0 is negative, this system has a bound state with energy given by that. But besides the bound state, and this is the thing that in the original problem, what we have been looking at, we have only been considering bound states. But there are also other states which are scattering states, and you can write them in this form. And this is actually quite suggestive that if we could write our solution in terms of this incident wave only, then one can quickly show that if you take the limit as V0 goes to infinity, then that thing vanishes. And this is the thing that we want to do. We want to show that eta xx when V0, when top coupling goes to infinity, actually vanishes. So this gives us some clue as to how to do that, but you can go further and look at, for example, the green, you can calculate the propagator. Again, the structure of the propagator will be similar to what we have, because you will have a term which represents free propagation, some vertex path, which will have some intermediate integral which you can do. Once that's done, then you can find what the bound states are, and which is what we do. There's a pole condition, look at the pole condition, find the bound state energy, the propagator gains, which is analogous to what we have been finding with the original problem. Now that we have done this simple quantum mechanical problem, then we can now return to the original problem. And what we do see is that we have an equation for this eigenspectrum is given by that, and we have only been considering solutions of this form. And these solutions are analogous to the bound state solutions that we were looking at. But there are also scattering states, and to find the scattering states, all we have to do is that we have to add to that solution. Consistency condition gave us a pole condition of that form. But we have to look also at the scattering states, and to add the scattering states, all we have to do is that we have to add simply the incident wave, or the solution to the free equation of motion, which is psi. So that, and then what one can do is that one can integrate both sides and try to solve for this quantity, take this quantity and plug it back into this equation. Then the equation then will be expressed in terms of, everything will be expressed in terms of this psi, which is the same thing that we saw for the quantum mechanical problem. Everything was expressed in terms of the incident wave. And then once that is done, then we can take the limit as lambda goes to 0. Doing that, we end up with an expression of this form. And if you take lambda to infinity, this term will cancel that term, and you end up with that this eta xx term is actually 0. So what we have shown is that this unwanted delta equals to 1 scattering state is removed at the boundary. As I was saying, the critical bilocal is actually finite, takes that form. You can even go further to have a check. You can just, using this expression, plug it into the expression for this propagator, and you can show that this is again 0. And in order for this to do that, this will involve cancellation between the connected and disconnected piece, something which was also said or expressed in the original paper by Klebanov and Klebanov. So if you go back to the bilocal nonlinear sigma model, the shift that I was mentioning will look something like that. So this gives you a hint as to how to construct the delta equals to 2 state using that. And you can check that if you compute it's not, you get a propagator of the delta equals to 2 state, and this propagator is actually, it will be orthonormal to the original fluctuations. In order for this to work, we have been using this result. So then, to summarize what we have found, we have obtained a bilocal relative quadratic Hamilton eigenfrequency for the lambda phi squared theory. This equation was shown to be equivalent to a pole condition in the vertex part of the covariant bilocal propagator, which also looked at a disconnected piece. Now, for negative top coupling, we found that there is this negative energy bound Tectonic state. And what we have shown is that there are also scattering states which we show that at the critical point, they vanish at the boundary, meaning that eta xx is 0 when lambda goes to infinity. In the infrared, the covariant bilocal propagator takes a finite form with the vertex part at 5 with the delta equals to 2. And then the operators of delta equals to 1 and delta equals to 2 also have the required property. So then there are certain open questions that we have been looking at. We want to have a better understanding of this whole condition. We have tried to come up with an oscillator expansion for the ON vector model, also the conformal algebra, and the map, even if it has been done in temporal gauge and light cone gauge, it's still in the UV, and we want to see if we can do it in the IR. In the beginning, I mentioned that there are two bulk reconstruction, one using exact Riemann normalization, the other using collective fields. We are trying to see if the two can be related to each other. I've also mentioned that if you couple the Chern-Simons, to these vector models, you have another sort of set of dualities. We want to see if we can set up a bilocal approach to these Chern-Simons coupled to vector fields. That would be all of them.
Mbavhalelo? Okay, that closes today's session. Let's thank Mbavhalelo again.